check, check, check. 1, 2, 3. 1, 2, 3, on peut dire.
Okay, so good morning, everybody. So we are here to listen to the defense of thesis by Aidan Meacham. So you have 45 minutes to present your work, and then we will ask questions in the general ranking order, reviewer first, and then the most distant one, I guess, examiner. So I guess we can start now, and please present your...
Wonderful. Well,
yeah,
yes?
We will start with Aidan, who is
Great.
farthest.
Yes.
Sorry.
Parfait. Alors, merci, Monsieur Président de Jury. And thank you all for being here. I believe it is still even before sunrise, so a huge thank you to all of you for being here in person. I'm so pleased to see you all and to present my doctoral research project entitled Toward Three-Dimensional Computation of the Energy Stress Tensor. Of course, this thesis is focused on room acoustics, which could be categorized as having a few main fields of study. Primarily, we are interested in what we hear. In this case, we are very interested in the process of pressure fluctuations in the air, interacting with the environment, reaching our eardrum, the cochlea, and eventually being transformed into a signal that our brains understand as sound. When an acoustic scenario is time invariant, of course we can represent it by measuring the response of the medium to an initial perturbation, such as a balloon pop. We call this the impulse response, and here is denoted in pressure, and it sounds something like this. Of course, depending on the space, they can vary quite widely. In this case, the impulse response you just heard is one of the hallways that we will talk about in the course of the thesis, but you can imagine what this space may have looked like. There's a lot of variation in room acoustics. That's what makes it so fun and so challenging as a field of study. Secondly, we're interested in how we perceive these sounds. We can divide up an impulse response into a few regions, that is to say, the direct sound, the early reflections, and the late reverberation, where each of these different portions of an impulse response give us perceptual clues about the source and the space that we're in. For example, the direct sound can tell us a lot about the strength of a source. The early reflections give us really strong cues about spatialization and localization, whereas the late reverberation really gives us a sense of envelopment, particularly in the long cases of reverberation time. Finally, we can talk about how we might model these phenomena, specifically with different types of methods. To start with, of course, we have geometrical acoustics, which are very popular for real-time applications, as it's very efficient at representing individual echoes. This is great, of course, for the early reflections, but it can become a little bit challenging as we get later into an impulse response when the count of echoes grows incredibly. For example, in this case, in a rectangular room, we can talk about the image source method, where we have a receiver in red, a listener here marked in blue, and 4 first-order image sources that correspond to the first-order reflections off of the rectangular room's walls. And as you'll see, the wavefronts emanating from these image sources travel along rays directly to the listener, allowing us to estimate the effect that each of those has at the source of the listener. Additionally, we can also approach acoustics by looking directly at the wave equation and approximating it. We could refer to this as wave-based acoustics, and often takes the form of finite difference, time domain, or boundary element methods. But in any case, these are methods where we are directly approximating the wave equation with some sense of approximation. Finally, we can talk about energy-based acoustics, which may be seen as a subset of wave-based acoustics, but where rather than directly modeling the pressure field, which is what we hear, we instead want to talk about the energy carried by these acoustic fields. And this is particularly useful in increasing efficiency when we're only interested in perhaps the noise. This, of course, the noise or the late reverberation portion of an impulse response, we might refer to as the stochastic reverberation. This is the portion in time and frequency where we have both dense modal response as well as dense reflections. That is to say that we have reached the diffuse field. Not all rooms are perfectly diffuse, but or diffusing, but as a general idea, we can say that many rooms reach this state such that we can characterize this final portion of an impulse response with a noise process. We might ask ourselves how we could directly model the shape that this noise process should fit, which is essentially asking the question, how do we do energy-based acoustics? To that end, in today's presentation, I'm going to discuss my work on the energy stress tensor method, which aims to do precisely that. First of all, we will, of course, cover the theory behind the method and the previous work performed on it. Then we will cover the validation of this method, specifically the frequency dependence of the method, the addition of a source term to the continuity equations, approximating it within a finite volume time domain scheme. And though we won't have time for it today, I also performed some research on RLizing these results. And then finally, we will talk about pushing this model toward becoming predictive and determining possible boundary conditions or field assumptions that we may make regarding the method through computing the terms directly in 3 dimensions. For a little background, let's start with the wave equation denoted in terms of a velocity potential psi. This means that the pressure of the field can be found by taking the temporal derivative, and the velocity can be found by taking a spatial derivative. If we are interested in the energy of this field, of course we can directly look at the potential and kinetic energy in terms of the pressure and velocity. This is great because it allows us to, for example, in a pressure simulation, to track the energy of the simulation and ensure that it is always conserved. The challenge, of course, is that in order to measure the energy, we do in fact have to compute the pressure everywhere in the space, probably using either geometric or a high-frequency wave-based approach. And this can be pretty computationally difficult. Instead, let's try a different tack. By looking at the Lagrangian of the system, here given by L, and using Hamilton's principle in order to look at the energy density contained in the field, here we will refer to as ETT, we can see, of course, that we return to the sum of the kinetic and potential energies. You may follow or be interested in the work in Morsen-Feshbach and Morsen-Ingerd, which describes this process in greater detail. And we continue with the idea that we can further develop this Hamiltonian idea to completely quantify the energy stored in the wave motion. The development of these terms gives us 2 continuity equations. The first relates the energy density, ETT, that I mentioned before, and the sound intensity, which we will call vector J. And the second set of equations relates the change in the sound intensity, J, to a term called the wave stress tensor _E. The important thing to note here is that we are, instead of trying to directly model the pressure field and compute these terms from that, we're going to try to directly represent this relationship in our model. Of course, you can give all of the terms with respect to the velocity potential. But the idea here is that these terms, in fact, change quite slowly in time. This is our primary advantage in this model, in that it should allow us to directly model the change in energy density in a space without having to perform an exhaustive pressure simulation. Finally, we can assemble all of these terms into the energy stress tensor, the subject of this thesis, which we call _T. As you can see, of course, we can go from our two conservation or continuity equations, simply writing them in the form of a tensor, where we can say that the divergence of the energy stress tensor is null. The advantage, of course, of the fact that we expect these terms to change very slowly with time, similar to the idea that the energy decay in a space is much smoother compared to the impulse response of the space. This means that in approximating it, we can use very large discretization elements, and furthermore, this allows us to use a very low sample rate. And this leads to a very large gain in efficiency over a traditional pressure-based wave equation solution. But of course, I have to hedge this with the fact that we are, of course, only modeling the stochastic reverberation. We can't make any claims about the direct sound or the early reflections. Previously, a doctor of Sorbonne Université, Hugo Dujardin, worked on this in his thesis, Diffusion acoustique dans les lieux de travail. And furthermore, with his co-authors, two articles that provide the basis for much of this work that we hope to extend. Previously, he developed this scheme in 1 and 2 dimensions. That is to say, the spaces that he studied were either very long or very flat. Furthermore, he developed a finite difference time domain numerical model in order to numerically approximate this scheme. And it was validated to in these spaces in the 1 kilohertz octave band. Our goal is to develop these ideas and extend them to 3 dimensions. As I discussed, Hugo Dujardin performed a dimensional reduction in order to model these spaces as either 1 or 2 dimensional, spaces that were very long or very flat. The idea here is that by integrating over the dimensions that are of the same characteristic length of the energy stress tensor, which I may remind you is quite large compared to a normal pressure simulation, this allows us to define some assumptions at the boundaries that help us close the system of continuity equations. Essentially, what we are saying here is that we are going to provide energy and momentum balances at the boundaries that allow us to quantify a proposed relationship between the energy density and the sound intensity components on the boundaries. We can do so by introducing alpha and beta, which we will call the absorption and scattering coefficients, giving us, of course, a relation between the incident portion of the sound intensity going into a wall and the energy, as well as being able to map the off-diagonal elements of the wave stress tensor in terms of the parallel components of the sound intensity in front of the boundaries. The problem, of course, with this approach is that in 3 dimensions, that is to say a space that exceeds the characteristic length of the energy stress tensor in all 3 dimensions, no such dimensional reduction is possible. Therefore, we must look for a different solution for spaces of these types. This also explains the difference or the challenge as we increase the number of 3 dimensions in the problem. Furthermore, there are some alternative ways to close the system of equations, and that is by making assumptions about a diffuse field. The first is the equipartition of energy. This means that energy is evenly split in the directions of propagation. So in 3 dimensions, evenly split in the x, y, and z directions. This effectively means that the diagonal elements of the wave stress tensor, which we would say Exx, Eyy, Ezz, are all equal, and they sum to the total energy density. The second assumption that we could make in a diffuse field is that of decorrelation. This means to say that the direction of propagation is evenly distributed radially speaking, and because of that fact, we can presume that there's no flux between the dimensions, as any flux would be resulting from a inequality between them. This effectively eliminates the off-diagonal elements of the wave stress tensor, the momentum flux terms. In both the 2- and 3-dimensional cases, at this point, these assumptions are required to close the system. Only the 1-dimensional case is capable of being represented without either of these assumptions, using only the energy and momentum balances at the boundaries. However, it has not yet been properly justified in the sense of exhaustively measuring and verifying that this behavior is the case in a wide variety of spaces. The first idea that we would like to address is the idea of the frequency dependence of the method. So previously, of course, it was verified in the 1 kilohertz octave band. However, we wanted to explore the entire auditory band to see in which frequencies this method is capable of modeling sound fields in real rooms. So the idea here is that we're going to match acoustical measures that we make in a real room and see whether or not, by varying the parameters of our simulation, we're able to recreate the same acoustical indices. What I mean to say by that is that for both the real and measured data, we're going to collect impulse responses and evaluate them in terms of their temporal decay, that is a T30, a measure of reverberation time, as well as the spatial decay, which in this case we will call the energy loss as a function of distance from the source. This, of course, is given in decibels per meter. We were interested in performing this study in 2 different hallways. The hallway on the left has alcoves all along its length along one side, whereas the other one is quite plain. It's quite straight along the length of the hallway. Members of the lab may know these 2 hallways quite well, I think. In both of the photos, we're at the halfway point looking down, and there's a slight change in the perspective given the lenses that were used. However, they are equal length, around 45 meters. So first we proceeded with data collection. First physically, we made measurements in these 2 hallways using an omnidirectional source and using the exponential sine sweep method. Our sweep length was 20 seconds and the sweep went from 20 hertz up to 20 kilohertz, and we measured many sample locations along the length of the hallway, both to confirm that the reverberation times are somewhat consistent, as well as to quantify the aforementioned spatial decays. Additionally, we performed simulations using a pre-existing 1-dimensional finite difference time domain approximation of the energy stress tensor. And the idea here is that we brute forced all of the combinations of the simulation parameters, which in this case are the absorption and scattering coefficients alpha and beta. This gives us a complete picture of the solution space for this model, given at least the lengths of these hallways, as well as the mean free path in each of them. I'll briefly present some of the measurements we made. For example, these spatial decays in the 2 hallways. On the left, we have the hallway with the alcoves, which you can see all follow a fairly similar slope, I would say, across all of the frequency bands. In the plane hallway, there's more variation in the slope depending on frequency. So we can already see that these two hallways have some measurably different acoustical characteristics. Additionally, we, of course, looked at our impulse responses, performed a Schroeder reverse integration, and calculated the T30s for each of these spaces. In the alcove hallway, you will see that at very low frequencies, there is a fairly long reverberation time, but above that, they're quite consistent. In the plane hallway, there's a little bit more variation, but of course, still a very long reverberation time at low frequencies. Fairly long, I should say, I suppose. We will take a brief detour for a moment to discuss the one-dimensional finite difference model that we used here. And I'd like to point out that the form of the equation that is represented in the finite difference simulations is called the Telegraph Equation. The thing I would like to point out here is that A and D, which are the modified absorption coefficients derived from the absorption and scattering coefficients, are in fact symmetric in this representation of the energy stress tensor. That is to say, with this formulation, we could switch them and have no meaningful change in the dynamics of the system. This is pretty strange because, of course, absorption and scattering, what we call these two terms, are definitely different physical processes. So why do they result in the same overall effect? In fact, this is a result of the dimensional reduction itself. We can say that scattering from the single dimension that we have reduced the problem to any of the other two neglected dimensions is also effectively reducing the energy in the same fashion that absorption would reduce the energy. So with that in mind, here are the simulation results with all of the combinations of absorption and scattering coefficient along the two axes. Of course, the first thing to note is that in both cases, they are highly symmetric as a result of the aforementioned symmetry between these two parameters. With regards to the temporal decays, we can see that there's a strong dependence on whichever of the two parameters is smaller. This, of course, is due again to the symmetry between the two, but also demonstrates that whichever of the two is smaller leads to an exponential increase as it gets closer to zero of the reverberation time as we approach the lossless case. So this makes sense. On the other hand, in the spatial decays, it's a much more smooth relationship. And one final idea to note is that if we specify a target spatial or temporal decay, so for example, let's say that we measure in one of the hallways 1.5 decibels per meter. In effect, we can draw an equipotential along the surface of these results that tells us all of the combinations of coefficients that were capable of matching that measure in the hallway. Then, by comparing the two equipotential surfaces for both measures in a specific frequency band, we can determine whether or not there is a combination of coefficients that is capable of representing both the temporal and the spatial decays in that hallway, in that frequency band. So, for example, in the alcove hallway in the 1000 hertz frequency band, we have two equipotential surfaces here within 10% of our measured value. The blue, of course, is the reverberation time, the T30, and the red curve is the spatial decay. Ultimately, these two green regions, symmetric for the aforementioned reasons, illustrate the existence of a combination of coefficients that satisfies both the temporal and spatial decay that we measured in the hallway in the simulations. On the other hand, in the 125 hertz octave band, there is no region, at least within a 10% threshold, where we can say that there is a combination of coefficients that fits both measures. Therefore, there is no, in the entire solution space of this model, there are no coefficients that are capable of representing the real measurements in the hallways. When we look in sum total in the two hallways, we can see that in the alcove hallway, beginning and above the 250 Hertz octave band, we have cases where the where coefficients were found satisfying the real measurements in all cases. However, in the plane hallway, only certain bands have regions where we found coefficients that correspond to the real measurements. One possible explanation for this is the alcoves in the alcove hallway generate far more reflections. That is to say, it is much more a much more diffusing or a much more mixing space than the plane hallway, which makes it could make it more suitable to be modeled with this stochastic method. Note that, of course, at this point, we don't know how to get the correct coefficients. This is why I say that we are working toward making this a predictive model. At this point, we are only capable of essentially performing analysis with the model. Next, let's talk about introducing a source term. Up until this point, we've said, of course, that the divergence of the energy stress tensor is null. This means, of course, that there is no change in energy in the system. In the case where we introduce boundary losses, of course there will be a change in the energy, but we can quantify that as being boundary losses specifically. This is, of course, equivalent to the classical initial value problem in acoustics, which is, generally speaking, what we use to generate impulse responses. If, however, we have the divergence not equal to 0, this implies that there is some creation or subtraction of energy. And we're interested in the form that this source term takes. We can return to the continuity equations, and by writing out all of the terms and proceeding with some algebra, we can in fact arrive at the following expressions, which of course we can recognize the wave equation. Since in the unforced case, we can say we have the relationship that these terms are equal to 0. This leads us, of course, to our original continuity equations, validating that fact. Of course, once we introduce forcing into the wave equation, we can carry these through with no changes, and ultimately, we can see that the source power, indicated by P, and the source intensity, indicated by Q, are effectively a volume velocity multiplied by a pressure and a volume velocity multiplied by a velocity. With this system of equations, of course, now we can proceed to a discretization, that is, an approximation. And in this case, we will use the finite volume time domain approach. Most recently, this has been spearheaded in acoustics by the Audio and Acoustics group at Edinburgh University, particularly Stefan Bilbao and Brian Hamilton. And it comes with a couple of very nice qualities. First is that, as mentioned before, by tracking the energetic quantities stored in the pressure, the velocity, and in the boundaries, we can ensure that the total energy of the problem is conserved to machine precision. Furthermore, it also gives us an opportunity to do some edge fitting, that is, to eliminate the staircase approximation that often occurs when trying to map say, cubic elements to a curved surface. You may have noticed this in the first animation of wave-based acoustics at the beginning of the introduction. Furthermore, at the time that we began work on this, and I think perhaps to this moment, there's no open source implementation of this method focused purely on acoustics. Therefore, it was one of our goals to develop this, both for the pressure case as well as for the energy stress tensor. For the energy stress tensor method itself, this also confers a couple of advantages. Because we have these very large elements, as we model more complicated three-dimensional spaces, this idea of edge fitting becomes more important. Today we won't really have to focus on it because the spaces that we are looking at are entirely rectilinear. However, it's a very important fact to keep in mind as more work is done with this method. Furthermore, the formulation of the boundary conditions in this method is particularly convenient, I feel, specifically for the extension to 3 dimensions compared to the dimensional reductions that were previously performed with the energy stress tensor method. And as mentioned before, in fact, it comes with a practical advantage that we can essentially share the same code base, the same concepts between a pressure velocity simulation as well as our energy stress tensor simulation, which was most important for the RLization that I will not talk about today, but nonetheless is quite useful. The main idea of the finite volume approach here is that we use the divergence theorem. That is to say that we're going to relate the change of the conserved quantity, in this case the energy density, to the fluxes through the cell faces of the corresponding quantities. That is to say, the sound intensity, either to a particular cell's neighbors or to a boundary. Therefore, as we take again a hallway as our main example, we quantify that as being a simple box and divide it up into rectangular solids. We can say that we have n cells called omega. For each of these cells, of course, by integrating over them, we can define an average energy density. We can define, of course, outgoing sound intensities, either to its neighbors, in which case it's indexed with the neighbor, or into the boundaries, in which case it's indexed with L. The source power and source intensity, of course, follow the exact same idea. Furthermore, because we have this one-dimensional collection of cells, we can effectively see that the sound intensity in the y and z directions, presuming that this long dimension is, of course, the x direction, are always going to be boundary, pointing into boundaries. This allows us to use the same energy and momentum balances that we described previously, but in this case they are indexed on an individual level for each of the cells. Furthermore, by eliminating the y and z directions in energy density, we are effectively at the same solution as before, but with additional flexibility in how we define our boundary conditions. So, as mentioned before, we essentially go from our continuous system, and by using the divergence theorem, we can go from the continuous equations to a completely discretized case where we have pulled out both the interior relationships as well as the boundary relationships into their own terms. Finally, of course, we can proceed with a temporal discretization, meaning that we sample all of the time-varying functions at a regular interval, and we replace all of the continuous temporal derivatives with discrete derivatives, that is to say, finite differences. Of course, in the simplest case of a forward difference operator, we can mention the case where we simply take the difference between two time steps divided by the time step between them. By offsetting the energy density and the x component of the sound intensity in the previous example by half a sample, we can formulate an entirely explicit solution. And by solving for the next step in terms of all of the previous steps, we can perform, of course, a two-step simulation of the system. We performed the same frequency-dependent study as before, but this time, in order to exercise the source term, we both made measurements with a dipole source in the alcove hallway, as well as simulating a dipole source in our simulations, and compared the results in the same fashion as before. One interesting thing to note is here that the elbow of the reverberation times is much sharper. However, in every case above 125 hertz, except with the exception of the 250 hertz octave band, we were again capable of modeling the spatial and temporal decays in the alcove hallway with a dipole source. Finally, let us turn to the idea of directly computing the energy stress tensor terms. Of course, at the beginning of the presentation, I talked about the fact that, in fact, we want to try to directly simulate the energy stress tensor. So why are we returning to computing it in terms of the pressure? This seems like a loss in efficiency. And indeed, it is. This is not something that we would want to do for, say, real-time simulations. In fact, this is effectively a way of trying to get around not having to do exhaustive physical measurement that might be possible in, say, a reverberation chamber or with roboticization, but instead taking a computational approach to look at the behavior of the energy stress tensor in various spaces to try to learn more about it and therefore improve both our confidence in the assumptions that we may make in modeling it directly in the future. So the idea here is that we are going to use now the pressure version of our finite volume time domain scheme, but at a fairly high sample rate. Our implementation is somewhat limited compared to the really high-powered GPU implementations out of Edinburgh, but nonetheless, taking into account a 1% dispersion error due to the cubic elements that we used, the maximum usable frequency that we had in this case was 1 kilohertz. Of course, we've seen in the previous examples that there is sufficient interesting representable behavior in this area, so we are confident that this at least will give us a clue into meaningful behavior of the energy stress tensor in this region. Furthermore, in this case, we provided impedance boundary conditions that met our measurements within the hallways, and of course we compute the velocity potential everywhere in the space for every single finite volume cell. As mentioned before, of course, we have already all of the terms of the energy stress tensor given in terms of the velocity potential. The only remaining challenge is, of course, to treat these in terms of the finite differences between cells, which we may approximate quite simply with the finite differences below. It is important to note that for a single cell, though, however, C sub j, psi sub j, this is effectively the instantaneous value of the energy stress tensor at a single position. This is actually quite useful, or rather has seen use in the literature, particularly as an estimator for direction of arrival. But as I mentioned before, we are interested in the slowly changing nature of the energy stress tensor. Therefore, we also introduce some spatial averaging over groups of cells in order to eliminate minute fluctuations in terms of space, as well as some temporal smoothing to eliminate the fine structure fluctuations that we don't expect to be as relevant for the evaluation of the energy stress tensor terms. Again, we return to the alcove hallway, but in this case, we were interested to evaluate the terms in different areas. That is to say, we were interested in different types of sections, that is, sections with 4 walls, the floor, the ceiling, and 2 walls. Sections with only 3 walls, the floor, 1 wall, and the ceiling. And sections with 5 walls. That is the floor, the ceiling, 2 side walls, and 1 extra wall in addition. The idea here is that we subdivided the entire hallway into these sections, and then for each of those sections, we furthermore divided it in 3 along each axis, such that the central collection of cells in each of these sections would be far from any boundaries. This is somewhat of an arbitrary choice, but the idea here was that we wanted to look in a region that was somewhat far from the boundaries. Of course, you could make any other choice about how you want to look at the energy stress tensor in terms of the pressure simulation. For example, you could look at the boundaries, and this is a topic for future research. However, we were interested to see along the length of the hallway, effectively speaking, how these terms changed in these different sections. So I will proceed with some preliminary results from this research. With the source 1 meter from the end of the hallway, and in this first case, looking in a passage type section 15 meters down the hallway, we can see 3 plots given in arbitrary units because they are coming from a pressure velocity simulation where we don't effectively know the specific pressure. In the first plot, we give the energy density as well as the directional components. And it's important to note here that for the most part, the x component is overlaid with the energy density, whereas the y component and z components are overlaid as well due to their similarity. In the second plot, we have the sound intensity. That is the x, y, and z components. And finally, we have the off-diagonal elements of the wave stress tensor, the momentum flux. Some general observations, beginning with this first example, is, of course, as mentioned before, the similarity between the energy density and its x component, as well as the y and z components. Furthermore, we can of course see a direct sound packet of energy, as well as 2 reflections. This of course makes sense as the wavefront first passes the receiver, returns, passes it again, bounces once more, and we see the final pass. And of course, the sound intensity changes sign upon reflection, particularly in the x direction. This is why it's so great as a direction of arrival estimator. One final thing to note is that the energy density and sound intensity are much larger in scale than the momentum flux. In fact, we did find that in many of these sections, some similar behavior could be noted. Specifically, as in the passage sections, that is to say, this type of section, the longitudinal, that is the x direction, and the transverse energy, that is the y and z directions, are somewhat in opposition. They go in different directions. To the contrary, as we move slightly further down the hallway to 18 meters into a junction section, we now see that the transverse energy is much smaller. This is already quite interesting. Furthermore, of course, as we've moved slightly further down the hallway, we can do a quick gut check to ensure that indeed, as we've moved further, there is a slightly more delay between these 2 reflections coming back from the source side end of the hallway. Finally, we can look in the alcove sections, where now the longitudinal and transverse energy are largely in agreement. Furthermore, of course, all of the terms are reduced compared to the region in both of the regions directly in the hallway, and we expect that this is likely due to the shadowing being in the alcove and perhaps losing a direct line of sight to the source. So some preliminary takeaways from this early information is, of course, that the x direction is dominant. This perhaps helps to support the case that we can, in fact, represent this hallway with a one-dimensional model without a loss of information. Furthermore, we have the possibility of the decorrelation assumption perhaps holding due to the relative size of the off-diagonal elements of the wave stress tensor. We furthermore note, but do not demonstrate here, the similarity of the different types of selections along the length of the hallway. However, this is the case. And we're interested in this changing behavior of the transverse components in the different section types. One possible interpretation of this may be related to the changing cross-sectional area of the hallway, which may provide an avenue for future research. So to conclude, we are getting closer to being able to perform predictive three-dimensional simulations of the energy stress tensor through our development of new tools, that is to say, RLization, as well as finite volume schemes and a source term for the energy stress tensor. Furthermore, we've improved our understanding of the behavior of this tensor in real spaces, both in accordance with its frequency dependence, as well as giving some of these preliminary results regarding the diffuse field assumptions that we may make. In the future, we hope that this can be useful for providing efficient and even real-time simulation of the stochastic reverberation with physically motivated boundary conditions. One possible idea for this is to look at a Riemannian space of a Riemannian tessellation of a space and how that affects the energy stress tensor. This is an idea that generalizes the image source method, which we saw at the beginning of the presentation. In that case, with a rectangular room, it's possible to tessellate the rectangular rooms on an infinite plane that is flat. However, as you can see here, with a five-sided room, we have to squeeze the second order reflections. This is essentially an effect of having a curvature of space. And one idea is that this is tied to the mixing that occurs in particular spaces and could provide information relating the geometry of a space to the behavior of the energy stress tensor. Furthermore, we would also like to generalize the computation of the energy conservation, but in this case specifically for the energy stress tensor, to furthermore bolster our confidence in the direct simulations that we perform, as well as to perform further research in the characterization of the simulation parameters directly in terms of the materials properties in a given space. So with that, thank you so much for being here. And I welcome any questions that you may have. Thank you.
So thanks for your